Hey, welcome to our explainer. Today we're talking about something fascinating. What happens after a fire? Because, long after the smoke clears, there's this huge, quiet question mark hanging over the buildings we use every single day.
And this is it. This is the big one for engineers and safety experts. Is this thing still safe? It's not about what you can see. It's about the invisible damage that could be a ticking time bomb.
All right, let's get right into it. To really get a handle on the danger here, you got to understand why fire is it's a completely different kind of problem for a building. It's a force unlike anything else they're designed for.
You see, structural engineers are used to dealing with forces they can predict, right? The weight of the building itself, the wind, even earthquakes. These are all things that push and pull. But fire doesn't play by those rules. It's what's called an accidental load, and it doesn't push or pull. It attacks the very heart of the materials themselves, changing them from the inside out. So what does that transformation actually look like? Let's play detective for a minute and look at the clues, starting with one of the most common building materials out there, concrete. Okay, so when a fire starts, the first part of this process is totally invisible. As that concrete heats up, all these little pockets of water that are trapped inside, well, they start to boil. They turn into steam. And that steam has nowhere to go. So the pressure inside the concrete just starts to build, and then it builds some more. Until boom. All of a sudden, that pressure is just too much to handle. The surface of the concrete can't hold it in anymore. And that's when you get a really violent failure. And this phenomenon, explosive spalling, is the first huge problem. We're not just talking about cosmetic damage here. No way. This process literally blows away the concrete's protective outer layer. And what does that do? It exposes the super important steel reinforcement inside directly to the fire's heat. Okay, so let's talk about that steel. There's this really common and honestly really dangerous idea that because steel doesn't burn, it's totally fine in a fire. But the truth is, it's way more complicated, and frankly, a lot scarier than that. Here's the wild part. Look at how dramatically steel weakens. It doesn't even need to melt. At temperatures that are pretty common in a building fire, we're talking around 550 degrees Celsius, steel can lose half of its strength. Just gone. It just quietly starts to sag under a load it was perfectly designed to carry before. And believe it or not, it gets even worse. While it's getting weaker, the steel is also expanding like crazy from the heat. This expansion acts just like a wedge, cracking the concrete around it from the inside. This creates a massive risk of a sudden, total collapse. It's just a devastating 1-2 punch. So, with all this going on, how in the world do engineers fight back? Well, they know they can't make materials totally invincible, so they design for something else, something precious: time. The whole strategy is to slow this destructive process way, way down. And that brings us to this key concept, a fire rating. Now, this isn't a promise that something is fireproof. It's not. It's a very precise, carefully measured amount of time, like, say, 2 hours, that a wall or a floor is tested to survive a fire while still doing its job. And to get that rating, a component has to pass 3 critical tests. You can remember them as R, E, and I. R is for resistance. It has to keep carrying its load. E is for integrity. It has to stop flames and hot gas from getting through. And I is for insulation. It has to stop the heat from spreading to the other side. So you see, the really crucial thing to get here is that the entire world of fire protection engineering is basically a race against the clock. The goal isn't always to save the building itself. The main goal, the critical goal, is to buy enough time for people to get out safely. But hold on, because the story is not over when the fire department puts the flames out. There's often this hidden partner in crime that comes out to play, one that works slowly, silently, and long after everyone thinks the danger has passed. And this silent accomplice has a name: desiccation. It's basically an extreme drying process. As the last little bits of moisture escape the fire-damaged concrete, the material itself starts to shrink on the inside. This creates a whole network of tiny, invisible microcracks that just silently eat away at its strength and durability over time. This really puts it in perspective, right? Fire is the sprinter. It's fast, it's hot, it's dramatic. The damage is obvious. But desiccation is the marathon runner. It's slow, it's persistent, and it's almost completely hidden. Its damage is measured in years, not in minutes. And this right here is the really dangerous twist. The fire comes in and does that initial brutal damage, right? It leaves the concrete all brittle and porous, and that basically sets the stage perfectly for desiccation to take over and do its damage much, much faster than it normally would. This creates this terrifying situation where a building can look totally fine on the outside, but it's secretly getting weaker every single day. So, when you're faced with a complex crime scene like this, with both immediate obvious damage and this long-term hidden threat, how do engineers actually figure out if a building is safe? How do they read the story that the structure is trying to tell them? Well, they basically become structural detectives. The whole investigation kicks off with what they can see with their own eyes: the color of the concrete, which can tell you how hot it got, and the patterns of the cracks. From there, they move on to more advanced testing, using special tools to measure surface hardness and look for hidden voids. But for the ultimate truth, they have to drill out core samples to test what the material's actual real-world strength is now. And all of this painstaking detective work, it all leads to one final verdict. The point isn't just to find the damage, it's to figure out if that damage can be repaired and if the structure can be given a second chance at a safe life for the people who will use it. Which brings us to the really big idea here. We tend to think of strong buildings as just being able to hold up a lot of weight. But true structural safety is about something much deeper. It's about the ability to resist fundamental change in the materials themselves, whether that change comes from a fast, hot fire or a slow, silent process of drying out. And that really leaves us with a final, lingering thought. A fire is obviously a dramatic and very visible event, but we've seen how its most dangerous effects can be completely hidden. It kind of makes you wonder, right? What other invisible forces, what other slow-moving changes are our homes, our bridges, and our cities silently resisting every single day?